Hi everyone, in this video we're going to start chapter 6, which is on discrete probability distributions. So we're going to begin by talking about discrete random variables. And we're going to begin with, in that section, distinguishing between discrete and continuous random variables. So we've talked about random variables in the past, but let's go over it. So it's a numerical measure of the outcome, and specifically now it's going to be from a probability experiment. So its value is determined by chance. And a lot of times we use letters like X to denote our random variables. So now the difference between a discrete random variable and continuous, if it's a discrete random variable, it has either a finite or countable number of values. And so if you plot them on the number line, there would be spaces in between each discrete random variable value. Think of just counting items. You would say 0, 1, 2, 3, and so on. The difference between that and a continuous random variable is that a continuous random variable has infinitely many values. So on a number line, it would be uninterrupted. You wouldn't skip 0 and then go to 1 and then 1 to 2. Everything in between can also be a value that your continuous random variable assumes. So you can have 0.01, 0.5, 0.99. Everything in between 0 and 1 can also be a value of your continuous random variable. So now let's look at an example where we distinguish between the two types of random variables. So part A, the number of A's earned in a section of statistics with 15 students is a discrete random variable because its values result from counting. You'd be counting the number of students. If the random variable X represents the number of A's, then the possible values of X are X equals 0, 1, all the way up to 15. This is saying that 0 students could receive A, all the way up to 15 students could receive an A, and it's only whole numbers or discrete values, because there's a whole number of, each person counts as a whole number. And then part B, the number of cars that travel through a McDonald's drive-thru in the next hour is also a discrete random variable, because its value results from counting. So X represents our random variable, and if we started counting cars, we could say X could be 0. If 0 cars pass through the drive-thru, X could be 1, and so on. Part C, the speed of the next car that passes a state trooper is a continuous random variable. So this is the first time it's not discrete, and that's because how speed is measured. If the random variable S represents the speed, the possible values of S are all positive real numbers such that S is greater than 0. So depending on the instrument that we use to measure speed, it can be accurate to the mile per hour or more accurate. It could be like 1 decimal place, 2 decimal places, so on. And so this is going to be a continuous random variable. It can take on any value that's positive in this situation. So next, let's identify discrete probability distributions. So the probability distribution of a discrete random variable, remember we're using X to denote our random variable, provides the possible values of the random variable and their corresponding probabilities. So a probability distribution can be in the form of a table, a graph, or a formula. So taking a look at this example, suppose we ask a basketball player to shoot 3 free throw shots. Let the random variable X represent the number of shots made. So if they're shooting 3, they can have X equals 0, so they missed all 3. X equals 1, so they made 1, all the way up to 3. So table 1 shows a probability distribution for the random variable X. Notice you have your random variable values, 0 through 3, and then the probability of that event or that outcome. So we denote probabilities using our P of X notation, where X is a specific value of our random variable. So we would say P of X as the probability that the random variable X equals little x. You don't have to really say little x, but just distinguishing between our capital X and our little x here. So for example, P of 3 equals 0.51 says that the probability that the random variable X equals 3 is 51%, or 0.51. So in other words, in this situation, the probability of making all 3 shots, free throws, is 51%. Now, rules for a discrete probability distribution. So we're going to let P of x denote the probability that the random variable x equals little x. Then, rule number 1, the sum, remember this capital sigma? This means the sum or summation of all of our probabilities has to add up to 1. And then rule 2, the probability of our random variable has to be between 0 and 1. It can also equaling 0 or equaling 1. See the equal bars underneath here. And we've seen these rules before for probability. All of the probabilities, when you add them up, have to total 1 or 100%. And then probabilities can be no less than 0 or 0% and no greater than 1 or 100%. So next example, which of the following is a discrete probability distribution? So here's a table, for example, and notice it has values for our random variable. It has probabilities of that random variable. But it's not a probability distribution because this last one right here. Remember, probabilities are always between 0 and 1. So this negative value means that this is not an accurate probability distribution. How about this one? We have our random variable values, their corresponding probabilities. But if we were to take the time to add up all these probabilities, it's actually greater than 1, which can't happen. So this is also not a probability distribution. Okay, let's take a look at C. We have our random variable values. We have their probabilities. And none of them are negative, so that's good. And if we add them up, they do equal 1. And so this is, in fact, a discrete probability distribution. Okay, next, let's graph discrete probability distributions. So we're going to graph the distribution probability distribution of this table right here from our free throw shots. Okay, and so it's discrete. So notice that the graph only has values at the actual random variable numbers. Okay, so it's not continuous. So at 0, this is actually right above 0. It's 0.01. So it's just barely above the horizontal axis. For 1 free throw shot made, or our value of 1 for our random variable, the output or the probability was 0.1. It says 0.10 here. That's the same as just 0.1. 2, for x equals 2, we have 0.38. Then when x equals 3, 0.51. Okay, next, let's compute and interpret the mean of a discrete random variable. Remember, the mean is the average. And so here's a formula for us. The mean of a discrete random variable is given by the following formula. And so just a couple of notation things to mention to you. This is mu. This is Greek mu. So mu sub x is going to be denoted for the mean. So when you see this, just think mean or average of your random variable. And it equals the summation, remember your capital sigma, summation of, and you're going to do what's in the parentheses first, x times the probability of x. So each of your random variable values, you're going to multiply them by their probabilities and then add them up. Okay, so x is the value of your random variable, p of x is the probability of observing the value x. So let's try this out. Compute the mean of the discrete random variable given in our previous table. And so the first two columns represent discrete probability distribution. So if I cut off this table with the first two columns only, that was our probability distribution table. And then now this new table, or sorry, this new column is just our calculation that we're going to need to compute the mean. So notice what we do. Each time we're going to take our random variable value and times it by its probability. So let's go to the last one. X was 3. We multiply that by the probability, 0.51. So we get 1.53. And then if you remember what we had to do next after we had all these values, it was going to be to add them up. So we wanted the sum of all these products. So you add up the first x value, first random variable value times its probability, plus the second random variable value times its probability, and so on until you've done all of them. And then that's going to give us our mean. which is 2.39, or about 2.4. So let's interpret the mean of a discrete random variable. We just calculated it using a formula, but we've learned about the mean in the past, so let's kind of compare what we've seen before with what we just did. So suppose an experiment is repeated n independent times, and the value of the random variable x is recorded. Okay, so you're just doing an experiment, and n represents how many times you did this. As the number of repetitions of the experiment increases, so the more times you do the experiment, the mean value of the n trials, so the average from the n times you did the experiment, will approach the mean of the random variable that we just calculated using the formula. So basically, we know that from the past, the mean can be found by adding up all of our values of our variable, of our outcomes, and then dividing by how many outcomes there were, the total. And so what this is saying, the more times we repeat an experiment, this value is very close to the value we calculated using our formula that we just did. And so the difference between x bar and mu sub x gets really close to 0 as n increases. So as more experiments are repeated, these two numbers get really close to each other. They're about to be equal, or they could even be equal. So let's take a look at our basketball player example from earlier. And let's say we ask the person to shoot 3 free throws, but do this 100 times. So we're going to compute the mean number of free throws made. Okay, so here's the outcomes of the 100 experiments. So first time the person shot 3 free throws, they made all 3. Second time they made 2. Third time they made 3. And so on all the way to the 100th time they did this, and they made 3. Okay, so in the first experiment, we went through some values, they made a 3, and so on. And so if we add up all 100 outcomes, divide by the fact that there was 100 times we repeated this experiment, we would get that x bar, or the mean, is 2.35. And if you remember, when we calculated, we got 2.39, or approximately 2.4, using our formula. So these are really close. 2.35 is really close to 2.4. And so these two figures are just the same experiment repeated twice. So here was a table of 100 values we saw a moment ago. This was just doing it again, so like another 100 times. And so notice what we have here. So the first time this experiment was done, the person made 3. The second time they made 2, and so on. And so it's taking the mean of those values, and notice what it's doing. It's approaching the same value from our formula, 2.4. Doing the experiment again, same outcome. After the more times we do the experiment, we repeat it, the value, the average, is approaching our theoretical value from our formula, 2.4. So what this is showing us is pretty much that the formula is very useful. We didn't have to do nearly as much work using our theoretical formula for the mean as we would have to do if we repeated the experiment 100 times and then added all of those up, all those values up. So next objective, let's compute and interpret the mean of a discrete random variable. So because the mean of a random variable represents what we would expect to happen in the long run, like if we keep repeating an experiment, it's also called the expected value, and we denote it E of x. So the mean is also called the expected value in this situation. So here's an example. A term life insurance policy will pay a beneficiary a certain sum of money upon the death of the policy holder. These policies have premiums that must be paid annually. So suppose an 18-year-old Mel buys a $250,000 one-year term life insurance policy for $350. Okay? So the probability that the Mel will survive the year is 0.998937, about 99.9%. Compute the expected value of this policy to the insurance company. And so let's break this into a couple steps. Step 1, because the probability that the person survives is this value we had earlier, the probability that they die would just be the difference between 100, the complement. So 1 or 100% minus the probability of surviving is how we get this one. If the client survives the year, the insurance company makes $350. which we can say that that's the value of our random variable, x equals 350. If the client dies during the year, the insurance company must pay $250,000 to the client's beneficiary, but still keeps the $350 premium. So we just do a little quick subtraction. They were given $350 for the policy, but they had to pay out $250,000. So they have negative $249,650. So the value is negative just because the insurance company had to pay out more money than they got. And so here's our probability distribution. Notice we have the values of our random variable, it's only two values in this case, and then the probability of those occurring. So then step 2, the expected value of the policy, and this is going to be from the point of view of the insurance company, is going to be the same as our mean. So remember we just talked about that. E of x, our expected value of our random variable, is the same as mu sub x, and using our formula from earlier, it's the summation of the value of our random variable x times its probability, and we do this for each x value. So we only had two x values, so 350 times its probability plus the negative 249,650 times its probability. When you add those up, you get $84.25. So a way to interpret this, the company expects to make $84.25 for each 18-year-old male client it insures. The $84.25 profit of the insurance company is a long-term result. It doesn't make this money on each 18-year-old male that it insures, but rather the average profit per 18-year-old male that it insures. And because this is a long-term result, the insurance idea will not work with only a few insured. So the idea is that the more people that the company can insure, the better they'll be financially. All right, our last objective is to compute the standard deviation of a discrete random variable. So we've seen standard deviation before, and we've had our formulas for it. And so for our discrete random variable x, we use little sigma for our standard deviation, and then we put our subscript x just to let us know that we are calculating the standard deviation of our discrete random variable x. And so our formula is, and we have two versions of it. In either case, it's going to be the square root of a summation. And in the first version, we take each value of our random variable, so that's x, and subtract the mean from it, square that, and then multiply it by the probability. And then once you do that for all of your x values, then you add them all up. And then very similarly, but just a modified version of the formula, we can square each x value first, multiply it by its probability, and then take that number, add all those up. Notice the summation is, there's brackets around just that part of the formula. So add all those up, and then subtract from there the mean squared. And then at the end, square root that. But a lot of times we use technology to calculate this, so we don't really have to do this by hand very often. And so, for example, find the standard deviation of the discrete random variable given in our table 1 here. This was our free throw example. And so we're going to go ahead and use our formula version 1. And with the unrounded mean, if we use that formula, we get 2.39. So we just plug in each of those values into our formula. And so here's kind of the work for it. If we have our x value, remember the formula said to take that number, subtract the mean, okay, and square it. So you square that quantity and then multiply it by the probability of that x value. Okay, so we get those numbers. We do that for each value of our random variable, and then after we found all those, we add them up. And then once we add them up, remember we still need to take the square root because that's our standard deviation formula has a square root in it. So our standard deviation of our discrete random variable x in this example is about 0.7. So another way we could do this is to use the other formula with our unrounded mean, 2.39. And remember in this version of the formula, we still had to use our x value and our probability, but the work was a little bit different. Square each x value, multiply it by its probability. We do this each time, and then add those up. So that's where the 6.21 came from. And then remember, from there we wanted to subtract the mean squared. So do the subtraction. We'll square this number first, do the subtraction, and then take the square root. We will get the same value, 0.07, or 0.7. Okay, so let's use software or graphing calculator to find the mean and standard deviation. So we did it technically by hand right now, but let's go ahead and use some software to do it. So this is going to be if you use your graphing calculator, and x bar represents our mean, our mu sub x, our theoretical value from our formula from before, and then our standard deviation is sigma sub x, so 0.7. So I'm going to go ahead and show you how to do this on the calculator, and then I'll also show you in StatCrunch. Okay, so let's go ahead and show how this works on the TI-84 calculator. I'm going to go to Stat, and I need to clear some lists because I've used them in the past. So I'm going to clear my list, and let's go to second, and I need list 1, and I'm also going to need list 2. So second list, and let's hit enter. Oh, I think I can only clear one at a time. So let's go to what we did. Let me delete one list. Okay, let's do that again for the second list. So stat, number 4 for clear list, and then I need my list. And I'm going to go ahead and clear list 2, and done. Okay, so that's out of the way. Now let's edit our list. So stat, edit, and let's enter our random variable values in list 1. So we had 0 through 3. Okay, and then let's go over to list 2. We had our probabilities. 0.01, we had 0.1, 0.38, and 0.51. Okay, so we can get out of here because we just populated our list. And so next, we're going to go ahead and go to Stat, and then over to Calc, and we want to go to one variable stats, which is number 1 here. And then we're going to go to our lists, so list 1, and then we're going to select list 2 for the frequency list. So then we're going to go down here and go to second list and select list 2. The probability goes under the frequency list. Then go down to calculate. And here we go. Here's our values. There's our mean, 2.39, and our standard deviation, 0.7. Okay, now let's do it in StatCrunch. So in StatCrunch, I've already inputted the values, our random variable, and then our probabilities. And this time how we do this one is we're going to go to Stat Calculators, and I'm going to go down to Custom. Okay, so my variable is in the row variable 1, and then the weight is the probability. So that's variable 2. That's column 2. And then we just hit compute. And there we go. So this is nice because it actually gives us a nice graph. And our mean is right here, and our standard deviation. Okay, that's it for this one. Thanks for watching.